Hi everyone! Today's topic will open one big chapter of statistics, a parameter estimation. The word estimation is equally important as the word parameter, because estimation is basically the maximum that statistics can do. Let's first review two steps in the process of estimation: measurement and inference. Typically, we measure some quantity in order to learn a certain new information. The process of extracting the information from the measured data is called statistical inference. For example, you might desire to estimate the activity of your new radioactive source that you just bought in your favorite second-hand shop yesterday. So you go to your shopping center, buy a Geiger counter and an atomic clock. You put everything on your desk at home and you check how many counts per second your Geiger counter registers. This is how you acquire data. However, the data doesn't tell you the activity. So you have to sit down, open your statistics book — we strongly recommend to use Glenn Cohen's statistical data analysis — and you read how to infer the activity from your data. You soon realize that it's not a straightforward task, and that there are many ways how to accomplish it. Two main branches are the frequentist and Bayesian inference. The frequentist inference is great, and it makes a perfect mathematical sense. Unfortunately, it speaks a language that is hard to understand. And more importantly, it doesn't answer questions that really interest you. Or it doesn't answer them directly. It's like a politician. You ask him whether the economics did worse this year than the last one. And he answers that if you repeated this year infinite number of times, then only in 5% of cases you would get data that is less compatible with the hypothesis that the economics work better than the data you actually observed. Wait, what? In the frequentist statistics, the true value of a parameter that interests you is not a random variable. It has some fixed value that you don't know, and you will never be able to determine it. You will never be able to learn the activity of your radioactive source. The best thing you can do in the frequentist statistics is to make an estimate and construct an interval that is narrow enough that it has a good chance, let's say 68.3%, to be covering the true value. On the other hand, in the Bayesian world, both data and true values of parameters are random variables. You are allowed to make very clear and conclusive statements like, "The true activity of my radioactive source lays in the interval I estimated with a probability of 68.3%. Furthermore, the Bayesian inference stands on your prior knowledge of the parameter value. This prior probability is nothing but your subjective opinion and has no equivalent in the frequentist statistics. In practice, a combination of frequentist and Bayesian approaches is used. Parameters are estimated using the maximum likelihood method, which is a frequentist approach. However, information from supporting measurements is included using constraint terms, which is a Bayesian approach. In statistics, there are two basic quantities that one tries to estimate: parameter values and intervals. Typically, if you are estimating a value of some parameter, you also need to estimate some confidence interval or uncertainty around the value in order to give your result some meaning. There are many types of parameters you might be interested in. If you are weighing your pet dog, then you are effectively estimating a μ-value of a probability density function which describes the precision of your scales. In this case, you are very happy if you just draw one number from this probability density function and you call this number your estimate of the dog's weight. However, this kind of estimate may be too crude for some situations. For instance, if you're weighing the Higgs boson, then you're estimating one parameter of a theory that has many unknown or not well-known parameters. In this case, you need to collect a large dataset, X vector, but you also need an intimate knowledge of the probability density function from which this dataset is drawn. Only then you will be able to estimate the theory parameter mass of Higgs based on your measured data. Regardless of what you do, you always need an estimator. Estimator is any function of data whose goal is to provide an estimate of your quantity of interest. For example, a very common and excellent estimator of the mean value of a probability density function is the arithmetic mean of measured data points. A completely inappropriate estimator would be, say, the smallest measured value. However, it's not always clear what estimator to use, and people define certain properties that a good estimator should have. Unfortunately, estimators you come up with rarely satisfy all the criteria, and you have to make a choice. We will denote estimator of an arbitrary parameter with a hat. Estimator of a parameter theta will be denoted as theta hat. Don't forget that every estimator is a function of data and, therefore, it is a random variable. It has its own probability density function with a certain mean value, variance, etc. Let's go through the properties a good estimator should have. First, consistency. A good estimator should be consistent. Mathematically, it means that if you acquire a certain amount of data events, n, then the value of the estimator becomes equal to the true value of the parameter when n goes to infinity. Mathematically, limit of theta hat for n going to infinity equals to theta. Second, bias. A good estimator should be unbiased. Bias of an estimator is the difference between the mean value of the estimator and the true value of the parameter. B equals to expectation value of theta hat minus theta. Here, recall what we said earlier, that an estimator is a random variable, so we can calculate its mean, variance, etc. Obviously, for an unbiased estimator, B equals to 0. It simply means that if we were able to repeat our experiment under identical conditions many times, then our repeated estimates would be spread around the true value of the parameter. If we are able to calculate the bias somehow, then we can define an unbiased estimator as theta hat prime equals to theta minus B. Of course, calculation of the bias is not always possible because the true value of the parameter must be known. In simple problems, however, it's possible to calculate the bias of an arbitrary value of the true parameter. Third, efficiency. Another excellent property of an estimator is efficiency. Of course, efficiency is an excellent property in general, but here we have in mind something different from how much work you can do in 1 hour or how far your car goes with 1 liter of petrol. An efficient estimator has the smallest possible variance. For a concrete experimental setup, no estimator can have a variance smaller than some lower bound. The bound is called the Rayov-Kramer-Frechet minimum variance bound, and we will look at it. Let xi is a set of equally distributed random variables. Xi is distributed according to f of x with parameter theta vector. And let's assume that the allowed range for xi doesn't depend on the parameter's theta vector. Then the variance of any consistent and unbiased estimator is always greater or equal to the inverse of the Fisher information matrix. Variance of theta hat is greater or equal to inverse to I of theta hat. The information matrix is given by the following formula. I sub jk of theta vector equals to minus expectation value of sum from I equal to 1 to n of partial derivative of log of f of xi with parameter theta vector over d theta j d theta k, and that in turn equals to minus n of integral of second partial derivative of log of f of x with parameter theta vector by d theta j d theta k times f of x with parameter theta vector dx. The integration might become very difficult. For this reason, there is a very common estimation that is very fast to evaluate. Let's say that we have a concrete set of values that were drawn from our PDF. In other words, we have a sample of values x prime I. Usually, these values are results of our measurement or come from the Monte Carlo simulation. Then we can estimate the information matrix by replacing the integral by the arithmetic mean over our sample. I hat sub jk of theta vector equals approximately to minus n times 1 over n times sum from I equals to 1 to n of second partial derivative of log of f of xi with parameter theta vector by d theta j d theta k evaluated at xi equals to xi prime. And that equals to sum from I equals to 1 to n of second partial derivative of log of f of xi with parameter theta over d theta j d theta k evaluated at xi equal to xi prime. Let's stress that one needs the true value of the parameter theta vector to calculate the Fisher information matrix. An approximation can be to use the estimators instead. Let's make an example. We will study very common estimators of the mean value and variance of an arbitrary probability density function. Let each value from a sample xi of size n be drawn from a probability density function f of x. The estimator of the mean value we will study is E hat of x, which can be also written as mu hat sub x, which equals to arithmetic mean x bar, which equals to 1 over n times sum from I equals to 1 to n of xi. It's fairly easy to calculate its bias. B equals to expectation value of x bar minus mu sub x. This equals to 1 over n times sum I from 1 to n of expectation value of xi minus mu x. Here, each xi can be treated as random variable, so its mean is mu x. So we will get 1 over n times mu x minus mu x, and that equals to 0. Very good, this estimator is unbiased. Next, let's check the variance of its estimator. Variance of x bar equals to variance of 1 over n times sum from 1 equals to 1 to n of xi, and that equals to 1 over n squared times sum from e equals to 1 to n of variance of xi, and that equals to variance of x over n. This formula is very well known. It implies that the standard deviation of an arithmetic mean decreases with the square root of n. Sigma sub mu equals to sigma over square root of n. Given that the variance of the arithmetic mean goes to 0 as n goes to infinity, and given that this estimator is unbiased, it's clear that it is also consistent. One more thing should be stressed. The variance of the probability density function f of x is often not known. Typically, we have to estimate it. Let's study the following estimator of the variance of probability density function f. Estimator of variance of x equals to 1 over n times sum from I equals to 1 to n of xi minus mu sub x squared. Calculation of bias of this estimator is quite straightforward. Expectation value of estimator of variance of x equals to 1 over n times sum from I equals to 1 to n of expectation value of xi squared minus 2 times mu sub x times expectation value of xi plus expectation value of xi expectation value of mu x squared. This equals to 1 over n times expectation value of x squared minus mu x squared, and this equals to variance of x. Unfortunately, we don't know the true value of the mean value most often. We can replace it by its estimator to get another estimator of the variance of our probability density function. Estimator of variance of x equals to 1 over n times sum I equals to 1 to n of xi minus x bar squared. Again, we can calculate the bias of this estimator. Expectation value of estimator of variance of x equals to 1 over n times sum from I equals to 1 to n of expectation value of xi squared minus 2 times expectation value of x bar times xi plus expectation value of x bar squared. This time, the calculation is much more complicated because x bar is not a constant. If we carried this calculation to the very end, we would get n minus 1 over n times variance of x. All of a sudden, we realized that this estimator is biased. Fortunately, we were able to evaluate the bias properly, and therefore we can correct for it. Let's define yet another estimator of the variance of the probability density function f. The estimator of variance of x equals to 1 over n minus 1 of sum I equals to 1 to n of xi minus x bar squared. Finally, we've got an unbiased estimator of the variance. And what about its variance? Obviously, the estimator is a random variable, and therefore it is distributed according to some probability density function. We will not attempt to derive the variance of the variance estimator, we will just write it down. Variance of estimator of variance of x equals to 1 over n times m4 minus n minus 3 over n minus 1 times m2 squared. The numbers m2 and m4 are central moments of the probability density function f. These are usually not known, so we make an estimator of the variance estimator by replacing the m's by m hats. At this point, a relevant question could be, what about the variance of the estimator of the variance estimator? Isn't statistics fun? Let's state clearly that you typically don't need to go through this whole chain. It's great because the chain is infinite. Your needs will be mostly satisfied by the estimators of mean and variance together with estimators of their variance. We can close this chapter by writing down the variance of the variance estimator in the case of the normal distribution. Variance of the variance estimator of x equals to 2 sigma to the power of 4 over n minus 1. Variance of the corresponding standard deviation can be derived using the standard procedure for transformation of probability density functions as outlined in the previous chapter. Variance of the sigma hat equals to sigma squared over 2n. You will quite likely meet this formula in your future careers. Keep in mind that in principle it is only valid for the normal distribution, although people often use it as an approximation for any probability density function.